So as soon as it's live streamed, okay, perfect. Okay, so welcome everyone, and thank you so much for being here with us today. As I was saying, this session is titled Ocean Science, Data and Research, and we have the privilege of being here with Dr. Push Baja, and I will now read his bio. So today we're joined by Dr. Push Baja, a research fellow and the head of the Blue Economy and Climate Change Cluster at the NMF. This session will aim to equip participants with tools and techniques they can use when studying ocean data and science. And now I will introduce a bit about the NMF. The NMF, or the National Maritime Foundation of India, was established in 2005 as India's first maritime think tank for conducting independent and policy-relevant research on maritime matters. While it is an autonomous think tank, its intellectual and organizational development is supported by the Ministry of Defense of the Indian Navy. Since its inception, the NMF has grown from a fledgling organization to an established intellectual institution with robust academic linkages within the country and overseas. Thank you so much, and I will now hand it over to our guest, Dr. Pushp, who will be sharing his screen.
Great, thank you very much, Anna. Let me just share my screen. And before I begin, I would like to thank the Airbus Foundation and the POP movement for giving me the opportunity to share my views at this Oceans Waves for Change camp. And since this is like a relatively cozy group of people, so maybe we can have sort of an informal session. And if at any point you feel like you want to ask a question, you can go ahead and maybe raise your hand, and I should be able to see it, and we can have a more lively discussion. So the topic that I will be speaking about today is understanding the ocean and climate connections. So to give you a brief overview of what the presentation will include, we will try to address these four key questions during the course of this presentation. The first one being, what are the major climatic changes that are occurring in the marine environment? How fast are these changes occurring and will occur in the future? And what will be the magnitude in the long term? Thirdly, what will be the impacts on India's holistic maritime security and the blue economy? And hopefully this would also provide some insights into how this might play out in other countries around the world. And lastly, what can or should we do in order to mitigate and adapt to these changes? So of course, if you're talking about climate change and its impacts on the marine environment, we have to start from the source of the problem. And we have to start by looking at the changes that are occurring in the temperature and the carbon dioxide. So at this point, let me just take a minute and ask some of you, if you could tell me, I'm sure that you have seen this graph in different formats. Maybe you have looked at this exact same graph, or you have seen some version of this while you have, while reading about climate change and how it's impacting the oceans and so on. So let me just ask you, what do you see when you look at this graph? What do you get from this graph? So any one of you could, maybe just chime in and share your thoughts on what do you see when you look at this graph? Yes, please, go ahead, Anna.
So it's very clear how the amount of carbon dioxide has never been this high, right? And also how the temperature is following the same pattern. So it really makes you think about the relationship between both of them.
Right. Anyone else would like to add any other insight from this graph?
Push, there's a message in the chat, the exponential growth of the emissions that are not going down.
That's correct. The growth, if you look at the rate of this change, you do see sort of an accelerating exponential growth. Anyone else? Ivan has his hand raised. Go ahead, Ivan.
Thank you. So we are seeing the chart of 1880s until now, but how about in like the historical records in all the history of, I don't know, the temperature register or the amount of carbon dioxide in the ice cores and all of that? How is it like in the past?
Right. Yes, we will. I'm glad you bring that up. We will talk about that in the next few slides. Okay, perfect. So we do have some initial insights. Let's try to see what we can gather from this graph. So it's like Anna said, it's pretty clear that the atmospheric concentration of CO2 is rising. And as Susanna said, that it is rising at an accelerating rate. We also see that the global average temperature is rising simultaneously, also at an accelerating rate. And there is significant year-to-year variability in temperature. So you can see that those black squiggles on the temperature graph, they correspond to the year-to-year variability, that some years it might go down, some years it might go up. And there is also similar variability in the concentration, in the CO2 concentration in the atmosphere, which was not shown in that graph because it was showing the average change. But there is similar year-to-year variability in CO2 as well. However, there is something still hiding in this image, because if you go back to this graph, you can see that the initial thought that you get by looking at this is that the temperature is kind of changing in a 1:1 sort of relationship with the carbon dioxide level. That if the carbon dioxide level has changed from around 300 parts per million to around 400 parts per million, that has led to a temperature rise of about 1 degree Celsius. So that it kind of gives you an impression that there is a 1:1 connection between temperature and carbon dioxide. However, that is not exactly correct. And we will see that, how that works out in the next few slides. So like Ivan was saying, that the graph was just showing us what has happened in the last few decades. But the planet goes much, it is much longer than just a few decades. Of course, it extends for millions of years. And in fact, to be exact, the history of our planet is around 4.5 billion years. But for humans, the most relevant period is the last few thousands of years. But if we try to go back and see how these things have changed in the past, and we can do that because of scientific methods that have allowed us to kind of indirectly measure what the temperature would have looked like some years in the past. So this graph, this is a very famous graph. Actually, it's taken from a 2008 study. It shows us how the temperature and CO2 concentration has changed in the past. And on the x-axis, you can see it goes from 800,000 years into the past and up to the present year, which corresponds to the 0. And then in the red, you see the Antarctic temperature, which is taken as sort of a representation of the global average temperature. And this is extracted from Antarctic ice cores, as Ivan suggested, that scientists can do that. And then the blue curve corresponds to the CO2 concentration and how it has changed over the last 800,000 years. Now, clearly, similar to what we saw earlier, there is a correlation between temperature and CO2 concentration. Now, they may have changed due to different reasons in the past, and it doesn't always have to be that the CO2 concentration changes first and then the temperature responds to that. It could be the other way around as well, that the temperature changes and in response to that, the CO2 concentration changes. So there is definitely correlation, and it can be either way. It can be CO2 changing first or temperature changing first. Now, if we come to the present time and if we look at where the CO2 concentration is at, we are actually somewhere around here. We have crossed 400 parts per million. In fact, we have crossed over 415 parts per million. Now, but the temperature is still kind of hovering around the same temperature. It has not responded to the way that it has responded in the past. And the reason for that is that this rise in CO2 concentration took place so rapidly that the temperature has just not been able to respond to that yet. So if we put this down into a few major conclusions, we can see from this graph that there is a sharp, unprecedented, at least in the past 800,000 years, rise in CO2 concentration. And this if we try to find a historical analog of when the CO2 concentration was as high as 400 parts per million, that was around 5 to 3 million years ago, during what is known as the Pliocene epoch. And during this Pliocene epoch, scientists have estimated that the global average temperature was around 2 to 3 degrees higher than it is today. And so if you remember from the first graph that I showed you, so far the temperature has only increased by 1 degree Celsius. So of course the question is, why is the temperature not shooting up? Why is the temperature not responding to this meteoric rise in CO2 concentration? And the answer actually lies in the oceans. The oceans actually absorb a large amount of the excess heat that is generated by greenhouse gases in the atmosphere. So this graph is showing the change in ocean heat content from the year 1960, from the year 1960 to the year 2020 on the x-axis, and on the y-axis it's showing the heat content. So we can see that during these last few decades, clearly there has been a relentless rise in ocean heat content. And this heat, as I was saying before, that the ocean actually absorbs around 90% of the excess heat that is generated by greenhouse gases in the atmosphere. And it also absorbs nearly 1/3 of the CO2 that is emitted by human activities. And I'm sure that some of you have already heard this before. Now, this heat that is absorbed has to be mixed because the ocean is so, the surface area of the ocean is so large, and also the depth of the ocean is so deep that this heat has to be absorbed. Once it is absorbed by the surface layer, it actually gradually gets mixed with the deeper layers through convection, through the ocean currents and so on, and it eventually comes in equilibrium with the atmosphere. Now, this entire process, because of the immense scale of the ocean, it can take several decades to centuries to realize the full warming potential of the CO2 molecules that are emitted into the atmosphere today. So to put this into to put this in a different way, it means that if we stopped all greenhouse gas emissions tomorrow, the global average temperature will still continue to rise because we have not yet seen the effect of the CO2 molecules that were emitted a few decades ago. And that's why when we look at the correlation between CO2 and temperature, we have to understand that when there is a change in the CO2 concentration, for that change to be reflected into the temperature, it takes several decades or even centuries for that process to occur. And of course, this additional heat has huge consequences for the temperature, which we will discuss in the later part of this presentation. But clearly, as the ocean absorbs all of this heat, it leads to an increase in temperature of the ocean water. So this graph is showing the change in ocean temperature going from the year 1880 to 2020. And this average corresponds to the average of the 20th century. So relative to that, the temperature right now is about 0.76 degrees higher than the average of the 20th century. Now, this was just a short historical background of how these things have changed in the recent past, and also what the changes have been like in hundreds of thousands of years in the past. Now, what is also important for us, as countries and also as an international community, we have to look at how these things are going to change in the future. And so this slide is showing us how the CO2 concentration is expected to increase in the future. So on the x-axis, you see the year going from 1980 to around 2100. That's the end of the century. And on the y-axis, it is showing us the emissions, the expected emissions from fossil fuels in gigatons CO2 per year. So in around 2016, we were at nearly 38, 37 gigatons of CO2 per year. And these graphs here, the red graph, the brown graph, and the orange and the blue, they correspond to the different scenarios that can, that will lead to an increase in the concentration of CO2 in the atmosphere. So some of you might already be familiar, but these scenarios are basically coming from the definitions that were put out by the United Nations Intergovernmental Panel on Climate Change, where the RCP 2.6, the terminology doesn't matter, it's just that this scenario corresponds to a scenario in which we take urgent transformative action to mitigate our carbon emissions. And then the RCP 8.5 scenario corresponds to the other extreme, in which we essentially do nothing to mitigate our emissions and we continue with business as usual. So the fact of the matter is that because we are already taking some measures to mitigate our emissions, we will likely not be following the business as usual scenario, but we will also not be following the best case scenario. So our emissions will most likely be somewhere in the middle, corresponding to probably the RCP 6 or the RCP 4.5. So, but just for the sake of argument, if we look at how the CO2 emissions are expected to rise in the RCP 8.5, this red curve corresponds to an expected increase by up to 1,000 parts per million of the CO2 concentration. So the rate of global carbon emissions is expected to continue to rise in a business as usual scenario. And all pathways that limit global warming below 1.5 degrees Celsius or even 2 degrees Celsius, which are the targets that were set in the Paris Climate Agreement, all of those scenarios assume large quantities of carbon dioxide will be removed from the atmosphere by 2100. So these basically correspond to the best case scenario that I was talking about, the RCP 2.6. So here you can see that it not only goes down, but it in fact has to go down to negative values, which means that we are actually extracting carbon dioxide from the atmosphere. And that is what is needed to reach the 1.5 and 2 degrees Celsius targets. But more importantly, if we don't do something about it, then the atmospheric CO2 concentration could cross 1,000 parts per million by the year 2100. Now, why is that relevant? Why is that number important? So if we saw what carbon emissions looked like in the past for 800,000 years, but in order to see something which resembles 1,000 parts per million, we have to go even further back in the history of our planet. So this is a reconstruction of what the climate would have looked like many millions of years into the past. In fact, it goes up to 400 million years into the past. And you can see that there are some phases here. This one corresponds to thousands of years. This one corresponds to millions of years. And this is hundreds of millions of years. So if we look at the projections that I talked about before, this 1,000 parts per million corresponds to this dotted line here. So right now we are at 400 parts per million. And as I mentioned before, the last time we saw 400 parts per million was somewhere during the Pliocene epoch, which was around 3 to 5 million years ago. So that would be somewhere around here in the green dotted area here. But if we want to find an analog for what the climate would have looked like 1,000 parts per million of CO2, that is probably somewhere around 30 million years ago. So the last time that the CO2 concentration was around 1,000 parts per million was 50 million to 30 million years ago during what is known as the Eocene epoch. And the global average temperature at that time is expected to have been somewhere around 13 degrees Celsius warmer than it is today. And at that level of global warming, it is safe to assume that no complex life form, including humans, can adapt to such dramatic climate change over such a short period of time. Like I showed you before, that rise in CO2 concentration has occurred so fast that it appears as a blink of an eye in the geological timescale. So in this short period of time, we cannot adapt to the changes that would occur at the level of, somewhere around 13 degrees Celsius of global warming. Now, this would of course translate into increasing ocean warming, as well as the atmospheric temperature increases, the ocean temperatures will also increase. So this graph is showing the projected ocean warming up to the year 2100. And again, this red curve corresponds to the RCP 8.5 and the blue curve corresponds to the RCP 4.5. So what happens as the temperature of the ocean continues to increase? What are the consequences of ocean warming? Well, the first consequence of ocean warming is what is known as hypoxia. So that is the amount of oxygen that is dissolved in the ocean water. The ability of the ocean water to dissolve oxygen reduces as its temperature increases. A perfect example of this is what happens to your soft drink or your soda when the temperature increases. When it's cold, it's all it's all fizzy and it's nice to drink. But then as the temperature increases, all of that fizz escapes, and then you're left with a flat drink. And so the same thing happens in any liquid. Actually in water, the same principle applies here. That as the temperature of the water increases, its ability to store gases decreases. So it can store less and less amounts of oxygen as the temperature increases. So this is what is shown in this graph, that in the RCP 8.5, which is given by the red curve, and the RCP 2.6, which is given by the blue curve, you can see that going further into the future, the dissolved oxygen will decrease as a result of increasing ocean temperature. The interesting thing about this, and something that we need to keep in mind, is that this is of course not going to happen uniformly across different parts of the world's ocean. So this graph in the white, it's showing the land areas, and the colored areas correspond to the ocean, the global ocean. But we can see that the level of change in oxygen content will not be the same throughout different parts of the ocean water. Some areas might see a very sharp decrease in oxygen, for example, the northern latitudes as shown here, and some areas might see, in fact, an increase in oxygen content, for example, some parts of the Indian Ocean region. So as I said, these effects will not be the same across different parts of the world. Now, another consequence of ocean warming is increased stratification. So now, what is stratification? Now, again, let me just take a moment and ask some of you if you can, have you heard of stratification? Can you tell me what is ocean stratification and why is it important for the oceans? Okay. Three people have their hands raised. I think Ivan had his hands raised first. So go ahead, Ivan.
Okay, just as a question, I'm not sure if this refers about the different so in biology there are different species living in different regions of the ocean, and each region has more oxygen and also has more light content, so, and temperature as well. So I don't know if you are referring to this, and if so, well, there's balances between the regions, and the top one, which is the one with the most oxygen and with more temperature, is the one where species thrive on regularly. There's the most species richness area, and well, from that, also the carcasses of the, I don't know, let's say the whales or the fish go to the bottom of the sea where other species are feeding from there. And also the top layer is really important because of the carbon, they act in a way as a carbon sink through the coral reefs and stuff. And well, yes, that carbon is going to end pretty much in the ocean floor later, but that's my insight.
Yeah, that's great. Are you a biology student?
Yeah, well, I'm a biologist, yeah.
Okay, perfect. Yeah, because that's spot on. Anyone else? Salma, you had your hand raised.
Thank you. I remember from my oceanographic classes that it is the process when deep layers go up and exchange nutrients and oxygen, and it is very important for the ocean upwellings.
Yes, that is correct. Kevin, do you want to add something?
Yes, same as what Ivan said and Sama, but also different concentrations, temperature, and density allows bottom layers to go up and upper layers to go down, and that's how different kind of nutrients get in different kind of structures of layers, and that's how yeah, species like whales get to in some places in some regions of the planet, and eat a lot because nutrients that are going up. So that's how it works.
Yes, yes, perfect. You between the three of you, you covered a lot of ground, and it's great. So you are, all of you are correct that stratification is actually a natural phenomena which occurs in the ocean. That because of the different temperatures and the different salinity of the salt content in the ocean water at the different layers, the layers can be separated from each other. And now, of course, this is not a very hard separation, but it's a separation nonetheless, because of temperature and salinity, it changes the density of water, and the different density of water separates into different layers in the ocean. So the top layer, which constantly exchanges with the atmosphere, so there is exchange of gases, there is exchange of aerosol particles, that happens at the top layer. And then just below that is the mixed layer, which is a more active, more turbulent layer. And then further below that is the deep ocean, which is much more separated and much calmer than the other, the surface layers and the mixed layer. So because of wind patterns and also because of ocean currents, some natural ocean currents like the thermohaline circulation patterns and so on, there is exchange between the top layer and the mixed layer. And this exchange, like some of you mentioned, this exchange is very important for the nutrients and the gases to mix between the different layers. And that is important for the marine biodiversity, because the starting from the microscopic phytoplankton particles to the bigger fish species, they all rely on these nutrients for sustenance. So this mixing process is again a natural phenomena, and it's very important for the biodiversity to flourish in the ocean. Now, what is happening because of global warming is that the temperature of the surface layer is increasing. Now, as the temperature increases, its density difference between the surface layer and the middle layer increases. So that creates more of a separation between these layers, and it makes it harder for them to mix with each other. Of course, this is kind of a simplified explanation of what increased stratification, how global warming is leading to increased stratification. There are more complex phenomena as well, but for the purpose of this discussion, the basic fundamental physical principle is that as the surface temperature increases, its temperature difference between the surface and the mixed layer increases, which makes it difficult for these layers to mix with each other. So this is just what I was saying, it's on the screen. And as this mixing decreases, we say that the ocean is becoming more and more stratified, and that has consequences for the marine biodiversity, which I will talk about in the next few slides. Now, so this is just saying the same thing in a different way. We also know that the chemistry of the ocean is changing because of global warming, because of the increased CO2 concentration in the atmosphere. As I showed in this slide here, that this top layer exchanges gases from the ocean to the atmosphere. So there is a constant exchange of gases like CO2 and oxygen. There is just through the simple process of dissolution, the ocean absorbs carbon dioxide from the atmosphere, and that produces, what does it produce? So since we have many biology and science students in the audience, what does CO2 produce when it is dissolved in water? There's a response in the chat. HCO3. It's H2CO3 plus, but close enough. So H2CO3 is a weak acid. That's what it produces. When CO2 is mixed with water, it produces H2CO3, and it's a weak acid, and that leads to increase in acidity of the ocean water, and that is measured through what is called a pH. That's the concentration of hydrogen ions in the water. So if we look at that, if we look at the projections for the pH going into the future, this graph is showing the changes in pH value from 1900 to 2100. Again, the red curve corresponds to RCP 8.5, and the blue curve corresponds to RCP 2.6. We can see that in the RCP 8.5, the pH is expected to continue to decrease. So a decrease in pH corresponds to increase in ocean acidity. Now, I'm sure that all of you are familiar that increasing ocean acidity has impacts on marine ecosystems such as coral reefs, and also other types of marine ecosystems such as mangroves. So this, again, we will come back to this in the next few slides. Now, in addition to the impacts of climate change that we just discussed, there are also some more direct impacts of human activities on the marine environment. And one of them is this, the release of untreated sewage and also industrial effluents that are released into the ocean water, which is leading to more and more marine pollution. And now this untreated sewage that is released into the ocean water, it actually contains large quantities of nitrogen and phosphorus. And some of you mentioned that the marine species require nutrients to flourish. Now, these are essential nutrients for the marine biodiversity. Nitrogen and phosphorus are essential for phytoplankton species. But just like too much of a good thing can be a bad thing, this introduction of artificial introduction of these nutrients into the ocean water is actually a bad thing for the natural balance of these nutrients in the ocean water. So let me ask you another question. Do you know what is eutrophication? Have you heard of the term eutrophication? It's when, yes, Ivan, the biologist will tell us what is eutrophication.
So it's when the water has a really high content of nutrients. Then there's some microorganisms that flourish on that, and then they start like taking all the oxygen later from that area, which leads to an hypoxic, as far as I can remember, hypoxic condition where organisms that need oxygen are going to die from, well, pretty much for lack of oxygen in their bodies.
Yes, that's exactly correct. So when there is when these nutrients are introduced into the ocean water, it doesn't have to be ocean water, it can be river water or lake water as well. When these are introduced artificially, that leads to an imbalance, and if there is excess of nutrients, that creates an excess of algal blooms, microscopic plankton particles, and when they decompose, so phytoplankton are not bad for the marine environment. They actually feed smaller fish, but when they are produced in excess, they cannot be consumed by fish species. So they're just left there to rot and die. And when they do rot and decompose, they consume oxygen. And so that temporarily creates a hypoxic condition because they use up so much oxygen that it leads to, it reduces the amount of dissolved oxygen in the ocean water or the river water. And that can kill off all the fish species that are present in that water. And this happens relatively quickly so that there isn't enough time for all the fish to move out of that location, and that can cause mass die-offs of fish species. So again, like I said, too much of a good thing can also be a bad thing. So if we try to summarize what we have discussed so far, all the ways in which climate change and also some human activities are affecting the marine environment, we saw that there is an increase in temperature, increase in stratification, also this nutrient-rich water that is introduced from human activities, and reduced dissolved oxygen in ocean water. Now, this has impacts for the phytoplankton species. Some of them we have already discussed, but if we look at them one by one, higher temperature generally leads to a negative impact on phytoplankton species. Some species are more resistant to higher temperatures, but for most species, it has a negative impact. Increased stratification, as some of you said, that it leads to decrease in nutrient availability at the surface, which again leads to a negative impact on phytoplankton species. Then this nutrient-rich water from human activities has a positive impact on phytoplankton. But if there is excess growth of phytoplankton, that has negative consequences for the larger food chain. And reduced dissolved oxygen, again, depends on some species, but for most species, it has a negative impact on the phytoplankton species. Now, the reason why phytoplankton are so important and why we need to understand them is because they form the base of the marine food chain. If we look at the marine food chain, it's the microscopic species like phytoplankton and zooplankton that form the base, and then there are larger creatures, and then larger microscopic creatures, and then small fish that then is eaten by bigger fish, and then ultimately by apex predators like sharks and so on. So if anything changes at the bottom of the food chain, that of course has implications for the rest of the food chain. But in addition to this, in addition to how the entire food chain ecosystem responds to climate change, there are also species respond to climate change at their individual level as well. So how do individual species respond to climate change? Marine species are actually very sensitive to environmental conditions, such as temperature, oxygen content, and other conditions, more so than terrestrial species. Now, we have observed behavioral and physiological changes in many species. For example, their breeding times, their feeding patterns, body size and body mass. It should say body mass, not body effects. But these are slow changes in the sense that it takes multiple generations for these changes to occur, and they cannot keep pace with the rate of change that we are currently seeing in the marine environment. There have also been distributional changes where marine species have moved out of their normal habitats and moved to different locations. Now, marine species can obviously move both horizontally and vertically, which is to say that they can go to different latitudes, or they can change their depth in the ocean to move away from higher temperatures and also lower oxygen content and go to more hospitable conditions. This has actually been observed in many places. So this graph, this slide is showing the change in some of these species in the North Atlantic coast of the US. So all of these, the x-axis in this graph corresponds to the latitude, and then the y-axis corresponds to the depth in the ocean. And all of these blue lines, they correspond to individual species. So we have seen, scientists have noticed that in general, the species are either going down, that is towards deeper ocean waters, or they are going towards the right, that is towards higher latitudes in response to increasing temperatures. Now, if we sum up what we have understood so far and how that will affect our, our societies and also our economic activities, if we look at the impacts on one hand, which include more frequent and longer marine heat waves, movement of marine species out of their natural habitats, expansion of dead zones in the Indian Ocean, for example. Dead zones are areas of low oxygen content, which we discussed, and then increased ocean stratification. Now, all of these impacts have consequences for maritime security and also for the blue economy. So, for example, these impacts will lead to loss of critical ecosystems, such as coral reefs. It would lead to decline in primary productivity. Primary productivity is basically phytoplankton species. This would disrupt the marine food chain and the carbon sequestration capacity of the ocean. This would also lead to decline in fish catch, leading to losses in the fisheries sector. It would, of course, lead to a decline in the natural appeal of ocean tourism, because these ecosystems like coral reefs are actually a large part of the tourist attraction. Also, these could increase the likelihood of intrastate and interstate conflict over fisheries and illegal, unreported, and unregulated fishing. Because if you imagine that as the fish species move out of certain regions, so if they were currently, let's say, a particular species moves out of its natural habitats in the Indian Ocean waters, and it moves out of the India's maritime zones, to, let's say, Bangladesh's maritime zones, or to Sri Lanka's maritime zone, or some other combination of such behavior, we can imagine that that could lead to a conflict between the two countries over who gets to claim those stocks. So these impacts and their consequences on blue economy and maritime security, they're often very interlinked with each other in complex ways. And these are not very easy to understand or even easy to deal with when we are looking at strategies to mitigate or adapt to these changes. So at this point, I know that we are maybe like 40 minutes or so into the presentation, so I've already taken up a lot of time, but I will try to maybe go through them, go through the rest of the presentation relatively quickly. So of course, the important question now is, well, what do we do about these changes, and how can we better prepare our economic structures and also our activities? The short answer is that there is no silver bullet. There are not even a few silver bullets. We need all the bullets and the grenades and the nukes. I mean, maybe, but the point is that we need all possible solutions, and we need a combination of all possible solutions to tackle this problem from every angle possible. So one way to look at it is that we need a three-pronged approach for continued global security and prosperity. The first thing that we need is deep emissions reductions, because we need to avoid some of the worst case scenarios that would occur if we continue emitting at the same rates that we have in the past. Then we also need simultaneously, we need large scale carbon drawdown, that is to reduce the existing carbon dioxide concentration in the atmosphere. And then finally, we need dynamic climate adaptation to adapt to the changes that have already occurred and that are projected to occur in the future. So now very quickly, when we are talking about emissions reductions, this graph is showing the global greenhouse gas emissions by sector, distributed by sector. So clearly we can see that energy gets the biggest slice of the cake. It corresponds to around 73% of our carbon dioxide emissions. Of course, energy itself is a very big collection of different types of forms of energy that we are using. It could be electricity, it could be fuel for our transport, or it could be energy used in our buildings for heating and other purposes, and so on. But talking about just electricity, we can of course harness the potential of the oceans to mitigate some of these emissions. And the oceans can be used in the energy, the forms of ocean energy can be used in the energy sector to reduce some of our carbon emissions. Now, I will not go into the details of this, but I would refer you to an article that was published by the National Maritime Foundation back in July last year. You can check this out on our website. But basically, the different forms of energy that can be harnessed from the ocean includes tidal energy, wave energy, ocean current energy, ocean thermal energy, and also offshore wind and solar energy. Now, all of these forms of energy are right now in very embryonic stages of development. Some countries are, of course, more advanced in this. For example, many countries in Europe have installed many of these ocean renewable energy technologies, and they're working fine. However, it's still not at the point where it's cost effective and competitive enough with other forms of energy. So there is a need for more research and development in this area to make them cost competitive. Then talking about drawdown of atmospheric carbon, there are many ways that are being explored to reduce carbon emissions by extracting them from the atmosphere. Of course, there are some obvious solutions, for example, reforestation and afforestation, because we know that there are natural sinks for carbon dioxide. Similarly, ocean is a natural sink for carbon dioxide. So there are also ocean-based carbon sequestration methods. There are some technological carbon sequestration methods like bioenergy with carbon capture and storage, and also direct air capture. But since the topic of discussion is the oceans, so let's briefly look at all the ways in which the ocean can be used, ocean and its ecosystems can be used to sequester carbon from the atmosphere. So we know that there are ecosystems such as mangroves, seagrass, corals, and phytoplankton species that do extract carbon dioxide from the atmosphere through this for the simple process of photosynthesis, just like any land-based plants do. But I also talked about in my presentation that all of these ecosystems are under threat from the impacts of climate change. However, there are people that are exploring ways in which this can be reversed. And in fact, we can enhance the ability of the ocean and its ecosystems to absorb more carbon dioxide from the atmosphere. For example, people are exploring genetically enhanced coral reefs, which are more resistant to temperature and to ocean acidification. Also, when it comes to seagrass ecosystems, there are ways in which we can basically use sea gardening to plant more of these seagrass meadows and increase their cover in the ocean. Then for mangroves, there is reforestation and afforestation. When it comes to phytoplankton species, there are some techniques that are in experimental phases right now, where you can essentially increase the nutrients that are available at the surface water, which can lead to more phytoplankton being produced in the ocean water. But we kind of touched upon this when we were talking about marine pollution, that if you artificially enhance the nutrients in the ocean water, that can have negative side effects. So if this approach is to be explored in the future, we have to look at these possible side effects that can come along with it. Now, finally, you don't really care about all of those things because you can't really do any of them, because you are still learning and you are still, finding ways in which you can contribute as, a young researcher or as a young conservationist or whatever form of career choice that you have, decided upon. But there are some things that you can do through this program of, Waves of Change Camp, and also in your involvement with the POP movement and the Irvis Foundation. So let's look at some of them. What are the challenges and opportunities when it comes to the marine environment and also climate change and the ways in which they are interlinked with each other? So the biggest challenge right now in our ability to tackle these changes is the lack of robust data records, data collection and data analysis. And finally, how do we disseminate that data to relevant stakeholders? So these stakeholders could be, the fisher folk, they could be people, they could be the seafarers who need to know the conditions in the ocean before they go out for their trip. And also the fisher folk, of course, need to know the ocean conditions before they go out fishing. So all of this data needs to somehow be translated into forms that can be disseminated quickly and efficiently. And in the first place, we need to have better data collection because the ocean is such a vast expanse and a lot of it is, open seas. So there aren't many ways in which we can access that data. So there is a need for innovative solutions in monitoring these variables such as ocean acidity, temperature, and also the biodiversity. There are so many species that are still undiscovered at different depths of the ocean and also in different areas of the ocean. Then we also know that local communities will play a major role in protecting and conserving critical marine ecosystems and local species. And in that sense, we do need to train them and make them more aware of the changes that are occurring and why those changes are occurring, so that they can they can respond to that appropriately. So in that sense, we need to build that capacity and their capability to understand these changes and also take appropriate measures. And in that sense, there could also be sharing of best practices. Some regions of the world and also in your own country, some areas might have found some solutions to deal with some of these changes, and that can be shared, of course, with other areas that are not so familiar with them. And this would go a long way in our conservation efforts. Finally, there is a need to create awareness about these maritime issues. I was born and raised in Delhi, and I'll just be honest about it. Before I joined the National Maritime Foundation, I was not as familiar with the changes that are occurring in our marine environment and also how we contribute to them. Whether you are living along the coast or not, all of your actions do contribute to the changes that are occurring in the ocean environment. And in turn, that affects the global climate. So for the people that are not directly related with the coastal environment, they may not be familiar with these changes. And so there is a need for us to create more awareness in that sense. So I hope that you can take something out of this presentation and apply that in your future endeavors with the POP movement and the Elvis Foundation. Thank you very much for listening, and I quite enjoyed interacting with you, and I'm open to any questions that you might have. Thank you.
Thank you so much, Push, for that amazing presentation. As always, I think every presentation, I have had the opportunity to attend one before by the NMF during the POP Festival, and it's just a completely different learning experience. And as someone who doesn't have a background in science, or someone who's just inclined by herself to work in this space, I think it's these kind of sessions that really teach us more about the ocean and our environment. So thank you so much for taking the time out. Like Push said, the floor is now open. If you all have any questions or any comments or thoughts you would like to share, we can have that right now. So you can either just unmute yourself or raise your hand. Anybody has any thoughts or questions? Yeah, Salma, please go ahead.
Thank you. First of all, thank you for the presentation. It was very interesting, all the topics. My question is, how can we extract or absorb carbon dioxide and greenhouses from the atmosphere and the ocean? It is similar to fossil fuels extraction?
Sorry, could you repeat that? You said to measure carbon dioxide in the atmosphere. Can you repeat the question?
Yes. How can we extract or absorb of these gases from the atmosphere and the ocean? It is a similar process to the fossil fuels extraction.
Right. Okay, I get it. Yeah, so I didn't get a chance to go through all of them, but there are many ways in which we can do this. Like I was saying, there are some nature-based solutions. For example, planting more trees is a solution in principle. But when you go deeper into it, you realize that if I plant a tree now, that would take many decades for it to grow to a point when it would be able to compensate for the CO2 that was being absorbed by a fully grown tree. Also, when you grow one tree in one location, that does not have the same effect as growing an entire forest in which has an entire ecosystem of trees. So that's the nature-based solutions is one way to go about it. There are also technological solutions. For example, there is what is called direct air capture. So there are techniques in which you can use chemical systems. There are some molecules that absorb carbon dioxide from the atmosphere. So you basically have like an instrument or a machine. The normal air goes in from one side, and from the other side, the CO2 removed air comes out. So the chemical material absorbs that carbon dioxide, and then you can concentrate it and store it underground or store it in some form, or actually use it in some product. And that way you are essentially removing carbon dioxide from the atmosphere. Now, if you go further into it, if you go deeper into it, you realize that there are some problems associated with that. Because the amount of carbon dioxide that is in the air is so less that the process is very inefficient. That because what we are talking about is 400 parts per million. That parts per million corresponds to, if there are million molecules of air, then that has 400 molecules of carbon dioxide. That's one way of looking at it. So the concentration is very small. So to extract that, it requires a lot of energy, and so it's an expensive process. Another way of doing this, so to solve the problem of concentration, let's say that you don't extract carbon dioxide from the atmosphere, but you extract it from the chimney of a fossil fuel powered energy plant. So if you go to that source, now that source is very concentrated because it's directly coming out of the chimney of the power plant. So if you install that same chemical material that you had and you put that on the chimney of a power plant, then that is more efficient. So there are many ways in which this can be done, and you can read further on this subject. And there are many ways in which you can extract carbon dioxide from the atmosphere.
Thank you so much, Push. I hope that answered some of Salman's query. Anybody else has any other questions, thoughts? I know we are 2 on the time, but if it's okay with everyone, if there are more questions, we can extend. If it's okay with Push, that is, if you can extend a little bit. Anybody has any other comments? I do see that in the chat. A lot of people are very thankful to you for this amazing presentation. But other than that, any other questions if anyone has? The floor is open. You can also put it in the chat if you would like. And before we close, I do see that Dr. Ash is also here. So if Dr. Ash has any comments or closing comments to share, we would love to hear that as well. I don't know if Dr. Ash is able to unmute himself. Okay, I'm not sure if he is able to. So Anna, is there anything you would like to say in the closing before we wrap up the session?
I just want to say thank you, Dr. Push. This was so amazing. I learned so much, and I find all the concepts that you've explained to us so clearly, and they're so interesting. And I would also like to thank all the participants who are here with us today. I hope you learned as much as I did. And also thank you so much for your participation and for being active throughout the session.
Great. Thank you very much. And I'm extremely glad that you all found it insightful and also useful. And I hope that I can stay connected with this Waves of Change camp.
Yes,
thank you.
Absolutely. If there are any other queries that come after the session, we'll definitely share it with you, Push. And once again, thank you so much for taking your time out, and and also to the National Maritime Foundation for always educating us and educating people who are new to this arena as well in such simplified ways and helping us become better. I think there is one more question. Chimitze, if you would want to unmute yourself, we can give you the space.
Okay. No, not necessarily. It's not a question. It's just to appreciate the POP family and also appreciate the presenter, Push Up. I can't really pronounce the name. It was wonderful. Myself is not so conversant with the area of presentation. So it was very insightful for me. I thank you all, and the effort we are making to push climate change issues is highly recognized and appreciated. Thank you, POP family. Thank you.
Thank you.
Thank you so much, Dimitri. Thank you so much, everyone, for joining once again. And we will shortly announce the date for the next session that we'll be hosting very soon. Thank you so much, Push, once again. And we hope to